Section 4.7 is the last section that we cover in chapter 4, and it's called logarithmic scales. And the situation is simply that sometimes there are units and formulas that are so big, some distance that's so huge that the numbers that you're dealing with are so large that it can be, unwielding. And so what you can use instead is by using a log scale, it actually compacts the numbers and then just makes them easier to deal with. So we're going to see some examples of where this is like in the world. Don't get too caught up in a lot of the notation. You'd really only care if you're going to see that in specific situations, depending on what your major is. So for example, the first one is a pH scale, and that's how acidic different solutions are. So things like a lemon juice, you could test the acidity of it. And it's really a simple equation here. It's just pH, that's one thing. And then it's just negative log of H plus. And you can see H plus is the concentration of hydrogen ions in the solution. So that's really all you need. If you have that, you just put it into there and you can find the pH of the solution. All you should really worry about is you've got the fact that 7 is kind of an indicator. If you get 7 as your pH, you've got a solution that's considered neutral. If it's less than 7, you're acidic. If it's more than 7, it's called basic. So there you go. So for this question that we have, find the pH of milk. It gives us the concentration of the hydrogen ions. And all we have to do is put those into this basic log equation here. So I'm gonna just write that better. So I'll put them here. So we have 4 times 10 to the negative 7. So that's a very teeny tiny number, which again is why the log is helpful to us. And so we want to put this into the calculator, and that's it. So if you have your calculator, you can do negative log, and then you can just do 4 times 10 to the negative 7. You can put that all into your calculator in one shot. That would be my suggestion. And if you do that, you should get, it looks like we're rounding to the nearest tenth here. If you do that correctly, you should get a pH of 6.4. And so that tells us that milk is just very slightly acidic. It's very close to 7, but it's not quite 7. It's a little bit less. So slightly acidic is milk. That's it. That's the whole thing. We have the same thing here. Now we just have the question of the opposite. So see, what is the concentration of hydrogen ions? Now you're given the pH. So now it's, like I said, the opposite, because you have that value, and then you need to find this H plus. Not sure why I did that. H plus. So in order to find H plus, all we really need to do here is just understand that this uses a log, and that log has base 10. So when you think about this, space-wise, let me kind of give myself a little more space here. When I think about this, I'll put the 10 right here. You don't need it. I'm just telling you that if you just see log, it's the common logarithm. But remember, this can be rewritten. That's what we need to do here. This can be rewritten. So the first thing I'll do is actually move the negative to the other side, because if I do want to rewrite it, I just want to have log. I don't want to have something in front of that log for the rewrite. Now, notice the right side says 10 to what power gives us H plus? And we're told that that's a negative 3.1. So we can rewrite it just like that. 10 to the negative 3.1 has to equal H plus. And then we just evaluate 10 to the negative 3.1. And just doing that on the calculator, will give us our answer. So 10 to the negative 3.1 gives us a small number, not as small, but 0 0, 0, 7, 9, 4. So really, I mean, the answer can be either one. This is a rounded version that I just came up with, or you have 10 to the negative 3.1, because that is a version in the scientific notation. So it's not uncommon to see that, just so you know. Just depends on what you're being asked to find, decimal, or you can leave it in the scientific notation. So another example would be the Richter scale. This is how the magnitude of earthquakes are determined. So you'll notice that the formula has M, which is the magnitude of an earthquake. It uses a log. Inside the log is I, which is the intensity, and that's measured by like a seismograph. You can kind of imagine that they read it, as you can see, 100 kilometers from the epicenter of the earth where the earthquake's happening. And you also have that being divided by S, which is the intensity of like the standard earthquake. And that gives you, you're being told that there's an amplitude there for that, like there's a value for there. So when we're being told find the magnitude of an earthquake that has an intensity of 6,000, they're giving us some earthquake, and that's the 6,000, the intensity of that earthquake. So we need to write that as 6,000. And depending, depending on the magnitude of the earthquake, that number is going to be, bigger or smaller. So what we also know that was given to us that might be hard to determine from the paragraph that you see there, but when we talk about S, we have what S is. We were given that. That's what S is, 10 to the negative 4 centimeters, this idea of a standard earthquake. And so now it's just a plug and chug. We're just plugging in the values, I, dividing that by S, and you put that in your calculator. So log of that whole thing needs to be inside the logarithm. Notice my parentheses there. And if you do that, you should get about 7.778, which typically earthquakes are to the nearest tenth, a 7.8. So that's actually a pretty big earthquake, magnitude of 7.8. Yeah, I mean, it's going to do some damage. So now we have the same thing, but the opposite. So in this case, we are given that the magnitude is 8.7. And our job is to find the intensity. You can see that we already have the the intensity of the standard earthquake. So if you want, plug those values in. It's going to be similar to the second example that we did. We're going to have to rewrite that to solve it for I, but you're welcome to try that and see what you get. So magnitude equals, and we have log. I'm going to write the base 10 just to remind myself that there is a base 10 there. I'm trying to find the intensity divided by our standard of 4. Okay. So rewriting this tells us that 10 to the 8.7 needs to equal I divided by 10 to the negative 4. And then to isolate our I, to get I by itself, we can multiply both sides by 10 to the negative 4 times 10 to the 8.7. That equals I. And so I equals 10 to the 4.7. And that's it. So you can just put that in the calculator if you want. And what you'll find is that it's about 50,118.7. So I want you to notice that the 7.8 that we just saw, its intensity was 6,000. This is 8.7, so it's a little less than one more on the Richter scale, but look at the reading on that. The reading on that is huge, as you can see. 50,000 is obviously a lot bigger than 6,000. So it's that idea of the magnitudes of 10, which is why we're using the logarithm. So just know that. So intensity is 50,000. Okay. And then the last thing we'll look at is the decibel scale. So if you've ever been to a big concert, put your face right next to the speakers. The idea is different sounds have different decibels. So as you can see, you have your very basic sounds, that are fairly audible, all the way obviously to sounds that are incredibly, incredibly loud. So we have this idea of B being the decibel level, and then 10 times log of, as you can see. So I is the intensity of the sound. And then we also have divided by I naught, which, not surprising, is this like reference intensity, similar to the S that we had before. So our first job is to find the intensity level of a front row concert if the decibel level was measured at 110 dB. So we're given, the idea here, not surprisingly, is that we're given that B is 110. And then we have this I naught, which is always 10 to the negative 12. So some very, very small number there. And then we can just plug this in and solve for our I. So that's the idea. So a couple steps, let me put that all in parentheses. A couple steps, we do want to get log by itself before we do anything else. So we're going to divide by 10. And that'll give us 11. And then we have our log I over 10 to the negative 12. But we don't want to forget, like before, we've seen this a lot today, but just a reminder, we do have base 10 here. So this allows us to do our rewrite. So now we can rewrite 10 to the 11th equals this inside, I divided by 10 to the negative 12. And then of course, we can get our I by itself by multiplying both sides by 10 to the 12th. So 10 to the 11th times 10 to the, negative 12 should give us I. And then in reality, these are the same base, so we can just add the exponents. And we get 10 to the negative 1, which is 0.0, nope, just 0.1. Because it's just 1. Okay, so it's just basically 1/10. So that is our intensity. So okay, so the intensity is 0.1. And then our last question. So it says the intensity level of the rustle of leaves is 1 times 10 to the negative 11, and we need to find the decibel level. So now we just need to find B, which means we must be given the other pieces of information. And we are, because in this case we are given our intensity here, and we are also given our reference intensity here. There we go. And, oh, I forgot my log. Gotta get that back in there. Myself a little more space. There we go. So it's a plug and chug, log. We can put this in the calculator all at once. That would be ideal if you're able to do that. And you should get 10 times. And then essentially what happens here is you end up with log, which is base 10 of 10. So if you were to take your calculator and you were to put 1 times 10 to the negative 11, and then you were to divide that by your 10 to the negative 12, you'll see that you should get 10. And so that tells us, pretty straightforward, that we know that log base 10 of 10 is just 1 because of our rule of the same base and the inside. And so 10 times 1 is just 10. So in this case, we have 10 decibels. And that's just dB for the rustle of leaves. And that is section 4.7.